No telescope in human history has ever taken a real photograph of an Earth-like planet orbiting another star. Not one. Every single one of the thousands of exoplanets astronomers have confirmed since the 1990s was found the same indirect way, through a shadow, a wobble, a flicker, never a picture. And the mission responsible for finding more of these worlds than any other instrument ever built, NASA's Kepler Space Telescope, never captured a single image of any of them either. It didn't need to. What it did, instead, quietly rewrote humanity's understanding of its place in the galaxy. And right now, in 2026, the successor missions built specifically to finally take that first real photograph are closer to launch than they've ever been. Stay with me, because the actual story here, how we went from 0 confirmed exoplanets to genuinely expecting billions of habitable worlds, is more remarkable than any single image could ever be. Let's start with how Kepler actually worked, because the method itself is almost more astonishing than anything it found. Launched by NASA in March 2009, Kepler was built around one deceptively simple idea. If a planet passes directly in front of its host star from our point of view, the star's brightness dips by a tiny, measurable amount for the duration of that transit. Catch that dip repeating on a regular schedule, and you've found a planet without ever seeing it directly, just by watching its shadow interrupt its star's light. Here's how small that dip actually is. If Earth passed in front of the Sun as viewed from a great distance, the Sun's brightness would drop by roughly 1/100th of 1%, an almost imperceptibly tiny flicker. Kepler was built with a single 0.95 meter mirror and a 95 megapixel camera, specifically sensitive enough to detect changes at that scale, and it pointed at one fixed patch of sky in the constellations Cygnus and Lyra, continuously monitoring more than 530,000 stars over the course of its mission. The results, once Kepler's data had been fully analyzed, were genuinely staggering. By the time the mission concluded, Kepler had confirmed 2,762 exoplanets, and its data ultimately contributed to a total exoplanet catalog across all missions that has grown past 6,000 confirmed worlds as of 2026. But the sheer number wasn't actually the most important part of what Kepler revealed. It was the diversity. Kepler's data uncovered hot Jupiters roasting at scorching temperatures just kilometers from their host stars, super-Earths larger than our planet but smaller than Neptune, an entirely new category of world that doesn't exist anywhere in our own solar system, lava worlds with surface temperatures hot enough to melt metal, and planets locked in stable orbits around 2 stars at once, real-world versions of Tatooine's twin sunsets. The galaxy, it turned out, was hiding. An entire catalog of genuinely bizarre worlds in plain sight. And Kepler's transit method, indirect as it was, proved sensitive enough to catalog all of it. But buried within that catalog of oddities was something considerably more consequential, a growing list of planets that weren't just strange, they were plausible candidates for actually supporting life. Kepler began finding Earth-sized and near-Earth-sized worlds, sitting inside what astronomers call the habitable zone, the specific orbital distance from a star where temperatures could allow liquid water to exist on a planet's surface, not too hot, not too cold, often nicknamed the Goldilocks zone. And this is exactly where Kepler's real legacy begins to take shape, because finding one such planet would have been remarkable. Finding dozens of credible candidates systematically across a fixed patch of sky, representing only a tiny fraction of our galaxy, is what actually changed the statistical picture of how common Earth-like worlds might be throughout the Milky Way. Let's walk through some of the specific worlds Kepler's data turned up, because these aren't hypothetical placeholders, they're real, named catalog discoveries that reshaped how astronomers think about habitability. One of the most discussed is K2-18b, a planet orbiting a red dwarf star roughly 124 light-years away, discovered during Kepler's extended K2 mission phase after a mechanical failure limited the telescope's original pointing precision in 2013. K2-18b is considerably larger than Earth, more accurately described as a mini-Neptune or sub-Neptune, but it sits within its star's habitable zone, and later observations using the James Webb Space Telescope detected signs of water vapor and other chemical signatures in its atmosphere, along with a controversial, still unconfirmed hint of dimethyl sulfide, a compound that on Earth is produced almost exclusively by marine life. That finding exploded across astronomy specifically because it marked one of the first times scientists had detected genuine atmospheric chemistry on a habitable zone world that Kepler's data had originally flagged, transforming the conversation from theoretical second Earths into a real distant planet with real measurable atmospheric clues, even if that particular biosignature debate remains scientifically unresolved. Then there's Kepler 186f, discovered in 2014 and still regarded as one of the most compelling Earth-sized candidates the mission ever produced. its size sits remarkably close to Earth's, and it orbits within its star's habitable zone. Later studies suggested its axial tilt might be stable enough to support long-term seasonal cycles and a genuinely stable climate over time, a detail that matters enormously because sitting in the habitable zone is only part of the habitability equation. A planet can occupy exactly the right orbital distance and still be rendered completely hostile by its atmosphere, its tilt, or its star's behavior. When orbit, tilt, atmosphere, and temperature all align favorably, the possibility of habitability moves from speculative to genuinely scientific. Among the more remarkable discoveries buried in Kepler's archived data was Kepler 1649c, a planet identified not during the mission's active years, but during a later reanalysis of older data using improved detection algorithms. What made it so compelling was how closely its numbers matched Earth's. Kepler 1649c is only about 6% larger than Earth, and it receives roughly 75% of the starlight our planet gets from the Sun, meaning its surface temperature, assuming the right atmospheric conditions, could plausibly land in a genuinely Earth-like range. Not identical, but close enough that its discovery made real. Headlines specifically because the numbers lined up so unusually well. Then there's the TRAPPIST-1 system, discovered using ground-based telescopes and later studied extensively by Spitzer and James Webb, rather than Kepler directly, but part of the same broader wave of habitable zone discoveries this era of astronomy produced. 7 Earth-sized planets orbit a single small red dwarf star, with 3 of them sitting within the habitable zone simultaneously, an extraordinary architecture that doesn't exist anywhere else we've found. The planets orbit so close to each other that, standing on one, the others would appear enormous in the sky, entire neighboring worlds hanging overhead like oversized moons. And because this particular system appears to be older than our own solar system, some of its planets may have had billions of additional years for conditions to stabilize, assuming life could take hold there at all. And then there's Kepler 452b, discovered directly by the original Kepler mission and widely nicknamed Earth's cousin in the press. At the time, it orbits a genuinely sun-like star and completes one full orbit in roughly 385 days, remarkably close to Earth's own 365-day year. It's somewhat larger and more massive than Earth, meaning surface gravity there would feel noticeably stronger, but its overall profile was similar enough to spark one of the strongest waves of public fascination in the history of exoplanet science, turning the abstract dream of a second Earth into something attached to an actual name, an actual distance, an actual candidate world, sitting roughly 800 light-years away. None of these discoveries came from a photograph. Every single one was reconstructed entirely from patterns in starlight, tiny, repeating dips measured with a precision that still genuinely astonishes engineers working in the field today. And that's exactly what makes Kepler's actual legacy so much more interesting than a single dramatic image ever could be. It didn't show us what these worlds look like. It proved through pure statistical rigor that worlds like this are common. Here's the number that actually changed the emotional scale of this entire field, more than any individual planet ever could. Based on Kepler's full statistical data set, astronomers calculated that roughly 1 in 5 sun-like stars in the galaxy could host an Earth-sized planet sitting within a temperature range compatible with habitability. Sit with that ratio for a second. The Milky Way alone contains somewhere in the range of 100 to 400 billion stars. Even using conservative estimates for how many of those resemble our Sun, that 1 in 5 figure translates into a potential population of billions of possibly habitable worlds in our galaxy alone. That's the actual moment Kepler changed everything, not through a single stunning photograph, but through pure statistics. Before Kepler, an Earth-like planet elsewhere in the galaxy was mostly speculation. After Kepler, it became a real, quantifiable, scientifically defensible possibility measured in the billions. Kepler's mission officially ended in October 2018, after the spacecraft ran out of the fuel needed to keep its telescope precisely oriented. NASA sent it a final set of commands, then let it drift silently into a safe, permanent orbit around the Sun, its work complete. But by the time it went dark, the fundamental shift in how astronomers understood our galaxy had already happened. Earth-like planets were no longer a fringe hope confined to science fiction. They were part of the galaxy's actual, statistically documented architecture. And this is exactly where the story picks back up right now in 2026, because the entire field of exoplanet science has spent the years since Kepler's retirement working toward the next real milestone, actually seeing one of these worlds directly, rather than inferring its existence purely from a shadow in starlight. That technology, called direct imaging, is extraordinarily difficult, because a planet is almost unimaginably faint compared to the blinding glare of the star it orbits, often billions of times dimmer, sitting close enough in the sky that a star's light completely overwhelms it in any ordinary photograph. Solving that problem requires purpose-built instruments capable of blocking out a star's glare with extreme precision while still preserving the ability to detect the faint point of light orbiting beside it. That's exactly what NASA's Nancy Grace Roman Space Telescope, currently scheduled to launch on August 30th, 2026, is carrying alongside its primary wide-field survey instrument. Its coronagraph instrument is a high-contrast camera and spectrometer specifically engineered to suppress a star's overwhelming light using advanced starlight suppression technology, allowing scientists to attempt direct imaging of planets and dusty planet-forming disks around nearby stars for the first time using a NASA space telescope built specifically for this purpose. This isn't Roman's primary science goal. Its main mission focuses on mapping dark matter and dark energy across billions of galaxies. But the coronagraph instrument functions as a genuinely serious technology demonstration, proving out the precise starlight blocking techniques that the next generation of observatories will depend on entirely. That next generation has a name, and it's the mission actually built from the ground up for exactly this purpose, NASA's Habitable Worlds Observatory, still in its early planning and design phase as of 2026, with no confirmed launch date yet, but with a single, explicit, stated mission unlike any previous NASA flagship telescope. Not mapping galaxies, not studying dark matter, directly imaging Earth-like planets orbiting Sun-like stars, and then analyzing the light captured from those images to search for actual chemical signatures of life in their atmospheres. If it succeeds, it would represent something genuinely unprecedented, not a shadow, not a wobble, not an inferred detection reconstructed from statistics, but an actual photon of light that traveled directly from another Earth-like world, captured by a human-built instrument carrying real information about that planet's atmosphere embedded directly within it.